Hello everyone, and welcome to the demonstration of TraceBrain. Today, we will show how TraceBrain provides a unified infrastructure to bridge runtime observability with trace-driven adaptation for autonomous LLM agents. As agent systems scale toward real-world deployment, their operational governance becomes increasingly difficult. We identify three main bottlenecks. First is context explosion. Traditional cumulative prompt logging introduces severe storage and transmission redundancy across long-horizon trajectories. Second is framework fragmentation. Framework-specific execution abstractions prevent standardized trajectory reconstruction and cross-agent analysis. Finally, the problem of passive logging. Most observability platforms remain passive logging systems, lacking runtime supervision and trace-driven adaptation workflows. These limitations create a clear gap between passive monitoring and active operational control. To solve this, we introduce TraceBrain's modular architecture. The ingestion layer utilizes a delta-based OTLP schema for efficient trajectory reconstruction without cumulative prompt duplication. The governance layer enables confidence-aware runtime supervision through an internal LLM-based trace evaluator. The cognitive layer provides hybrid semantic lexical retrieval and automated curriculum synthesis for trace-driven adaptation. Let's see this closed-loop architecture in action. To demonstrate TraceBrain's capabilities, we present a system demonstration involving a multi-agent coordination failure. Our setup features a coder agent and a reviewer agent iteratively validating code. We will walk through how TraceBrain handles this anomaly through 4 steps: detection, diagnosis, supervision, and adaptation. We are now in the TraceBrain command center. As our agents operate in the background, their activities are streamed instantly to the dashboard. As you can see, a new execution trajectory has appeared. During execution, the coder and reviewer agents entered a cyclical negotiation loop caused by semantic misalignment. TraceBrain ingests these interactions via the delta-based schema and automatically flags the trajectory as anomalous, categorizing it as a logic loop. Instead of failing silently, the system triggers a runtime escalation. We now enter the Trace Explorer to investigate. Unlike scrolling through flat logs, TraceBrain visualizes the interaction as a hierarchical execution graph. By expanding the spans, the operator can clearly identify the specific execution step where the interaction divergence emerged. We can see exactly where the coder misinterpreted the reviewer's constraints, leading to the persistent coordination loop. To understand if this is an isolated incident or a systemic issue, we consult the AI Librarian. Powered by our hybrid retrieval engine, it allows operators to query operational memory using natural language. The system confirms this is indeed a recurring pattern. It found 3 recent traces sharing the same logic loop classification, confirming that the coder consistently misinterprets the constraints. We now move to supervision. Because the internal trace evaluator assigned a low confidence score to this ambiguous failure pattern, the trajectory is prioritized for expert validation. We utilize uncertainty-driven supervision. The system provides a pre-populated assessment. The human expert simply reviews and validates it, structurally embedding the supervision signal with minimal manual effort. Finally, we shift from governance to adaptation. We initiate the automated curriculum synthesis process. In the background, the cognitive layer mines these validated failure patterns. Rather than proposing isolated code fixes, the system abstracts these failures to synthesize structured remediation tasks. The generation is complete. TraceBrain has produced a prioritized set of 5 training tasks. Notice how these scenarios directly address the semantic misalignment, training the system to enforce consensus protocols and prevent behavioral regression. With a single click, we export these reconstructed trajectories as JSON artifacts, ready for downstream adaptation pipelines. To conclude our demonstration, we evaluated TraceBrain's infrastructure scalability and supervision benchmarks. First, regarding storage efficiency, our delta-based schema achieves an approximate 100 times reduction in storage overhead compared to naive logging. Second, this optimization does not sacrifice speed. Reconstructing a full execution context with 500 spans requires only about 3.6 milliseconds on the client side. Third, for retrieval, the system maintains a stable median hybrid retrieval latency of approximately 97 milliseconds at a scale of 100,000 traces. Finally, regarding labeling efficiency, our trace evaluator achieved an 89% high-confidence automatic acceptance rate and a priority precision of 0.93. The key takeaway is that TraceBrain effectively balances storage efficiency, scalable retrieval, and uncertainty-aware supervision within a unified trace infrastructure. In conclusion, TraceBrain provides a practical infrastructure for the management, supervision, and adaptation of autonomous LLM agents. It introduces a standardized, delta-based OTLP schema. It enables trace-driven governance through runtime escalation and uncertainty-driven supervision. And it transforms historical traces into reusable operational memory and structured training artifacts. Ultimately, TraceBrain shifts the paradigm from passive observability to trace-driven governance and adaptation. You can scan the QR code to access our open-source repository. Thank you for your attention.